Hello, I'm David from David Savory Electrical, and tonight I'm talking about the Megger MTB7671/2 check calibration tester. And here it is, up close and personal. What is it? Well, it allows me to test my multifunction testers, my Megger and my Fluke, to make sure that they are operating within prescribed parameters and that they haven't gone a bit screwy since their last calibration test. Now, obviously we have to have our testers calibrated every year, whether we like it or not. Unfortunately we don't, because it's often quite expensive to do. The first time I got my Megger tester, the first tester I got, I took it for proper calibration. It went off to a lab, they had it for several days, it was tested under climate controlled conditions, and it was horrendously expensive. These days I tend to take it to City Electrical Factors or Edmondson's or whichever supplier happens to have an open day when they are offering calibration services, and it happens to be calibrated usually by some sweaty bloke sitting in a hot non-climate controlled office out the back there, where the tester's just come off the van, hasn't had time to acclimatise, and they just run it through whatever tests from whatever tester that they run it through, and at the end of the day I get a certificate with their signature on saying that it's all good and above board, which is fine because it shows I've done my due diligence, and it keeps the likes of NIC, EIC happy when they come to audit me. However, to maintain my NIC, EIC approved contractor status, I have to take the additional step of having my testers checked at least once a month. Now I can do that myself with this baby, and I've had this about a year. It must have cost 300, 350 quid. I really can't remember what the price was now, so it was fairly expensive. And I try to test my testers. I was starting off doing it once a week. That seems to have slipped a bit now, and it's generally probably on average around once a month. But basically I hang my Fluke and my Megger off this. This squirts out some test numbers, and both the testers should come back with much the same results, certainly within the tolerance of the whatever this device is putting out. And I then keep all that data stored in a spreadsheet, where I can see what numbers I got on what dates, and it should all match and correlate. And when NIC come round to visit me and audit me, they don't give me any kind of slaps on the wrist, so they're all happy. So let's have a look at this from right to left. We start off with the dead tests. We've got continuity and insulation on this side, so this will obviously send out some resistances which should match what we see on the screen of the tester. Insulation resistance testing, obviously when we squirt a DC voltage at 250, 500 or a kilovolt into the thing, then we expect to see certain numbers come back. We have a voltage test point here where we can plug in our probes to make sure that we're getting somewhere in the region of 220 to 240-ish volts here in the UK. And on this side of the board, this is where we have our live tests. So on the left we've got RCD tests for 10, 30 and 100 milliamp RCDs, and on the next to that, on this side of the board, we can do our fault loop impedance and prospective fault current tests. For the live side of the board, I don't think you can actually see that on the video, let me just rotate that around a bit. We have a socket here that we plug our test lead into, and that socket is dead until I close the flap here, and these two prongs short out the link to the socket and make it all go live. So let's plug in the tester and do some tests. Okay, well, do excuse the glass of wine, although I won't, excuse me. Oh yeah, it is a weekend evening, it is the autumn, so that means that the wife's watching Strictly in the other room, and I can't stand Strictly Come Dancing, so rather than being in there watching the audience clap along to whichever B-list celebrity is prancing around the dance floor this week, I should be in here playing with this stuff. And this stuff is a Megger MTB7671 multifunction tester, which is an old girl but damn near bulletproof. So I'm using that tonight for two reasons. First of all, it's probably got a bit of a better display than the Fluke for this sort of purpose. It's a much simpler display, so it probably comes out better on the video for explanatory purposes. But also it supports RCD auto testing, which my Fluke 1651B doesn't, which is a bit of a pain. But we're going to be doing some RCD auto testing later, so we can see that in action. And we're going to start off by switching the tester on, and the first thing I want to know is what's the battery doing, and we're reading 9.9 volts. Now I don't like the Megger to fall below 9 volts. I use lithium ion rechargeables within it, so if it drops too low, I'll take them out and I'll charge them up. 9.9 is fine for the moment now, so that's another week where I don't have to worry about doing that. And what we're going to do is we're on the voltage setting, so we're just going to plug in the probes, and obviously, like I say, we should see somewhere around the 240 volts, because we're in the UK here. Now, the dead tests aren't going to make any use of the blue neutral probe. We've only got the brown live and the green earth probe in there. So in order to check that we haven't got any problems with our third lead, our neutral lead, it's best every now and again to rotate one of these cables with the neutral, just to make sure that that in itself is healthy and isn't wearing out, hasn't got any high resistant joints around the probe plug or anything like that. So we should get the same sort of readings regardless of which probe we use, but it's good to rotate them around a bit. So that's high voltage, and what I do, of course, is I've recorded that on the spreadsheet to say the Megger's recorded 240 volts there, and when I plug the fluke in later I want to see the same sort of number. Now I'm going to switch to continuity, and I'm going to switch this to 5 ohms, and obviously on the display there we should get around 5 ohms. Now the sharp people amongst you there will go, hang on a sec, you didn't null your probes. Of course I didn't, did I? Naughty boy. So before I do that, I really ought to make sure that I'm getting a 0 reading before we start. Yeah, we are. Jolly good. Okay, so let's go back to that. And we should get, like I said, somewhere around the 5 ohm mark. Now it's reading 5 ohm on the nose, but this tester does have a certain amount of tolerance, and I happen to know that on the 5 ohm setting we should be seeing 4.85 to 5.15 ohms. So there's a certain range that this thing should be putting out. Incidentally, I mentioned earlier about the need to still calibrate your testers. What my NIC instructor did tell me was I don't need to calibrate this thing here. The testers will keep that in check. And so long as the testers agree on the numbers that this is pumping out, then that's fine. It doesn't really matter if this goes out of calibration to a certain extent. So long as both testers are reading the same kind of results, then we know that this is putting out a constant number. If obviously the testers disagree on the output of this thing, then we'll have to have a closer look at the leads and the testers themselves, and maybe send them off for checking to make sure that they're still in calibration. I haven't had any problems with calibration. They do take the odd fall off the ladder or end up out in the cold on dusty first fix sites. So despite appearances, and it is in pretty good nick still after all these years, they do get kicked around a bit, so you never know when something's going to not quite work the way it should. Now I've just switched that to the 0.5 ohm range, and again we're getting somewhere close to that, 0.48. It's within tolerance, so we're all right on that one. And then we're going to switch now to the insulation resistance testing. There is this V-test and I-test thing here. You know what, I can't remember what they do now, I never use them, but if I remember rightly, one or both testers didn't like that test. I can't remember what the issue was now, it's about a year ago that I was playing with that. Anyway, we'll skip that and we'll go on to the 250 volts IR test. So we're going to squirt 250 volts DC into here. If it's successful, we should get a 0.25 on the display, and the two green lights should light up to indicate that the voltage and the current expected from the tester are okay, and that is exactly what we have got. Switching it to 500 volts, we should get a 0.5 on the display, and again the two green lights, and we can also test it to a kilovolt. Now this particular tester is going to sound a bit of an alarm when I select the kilovolt range. The fluke doesn't, but this one does. It just beep a few times before it actually does the test. It says, are you sure you want to squirt 1000 volts into this thing? And in this case, yes we do, and we get the reading we expect to get, which is 1.00. Jolly good. Now we have two more tests that we can do here, and I'm just going to switch this back to 500 volts. Although the numbers that we get on here should be the same, regardless of whichever setting we use on there. This is the 9 Megger ohm test, which should give us 9 Megger ohms, and the turning the wrong dial. The 90 Megger ohm test, which should give us 90 Megger ohms. Again, there's a certain tolerance there that we're allowed. We're getting 90.3. If I just refer back to my spreadsheet, I can see that 87.3 to 92.7 is what the manufacturer says that this should be putting out. So we're on the money there. Super stuff. So what I'm going to do now is I'm going to take out the test leads, and I'm going to plug in my plug lead to start doing some live tests. Okay, we're ready to start doing some live tests. Now before we do, I'm just going to turn off this light here. Just to show you, you can see some LEDs, well just about see some LEDs on the tester here. Let me just zoom in a bit, see if I can get them a bit better. We have a red LED here to indicate that there's power to this socket. We have a red LED here telling us that we have AC voltage coming in. And we have two green lights showing us that there's no polarity reversal and that we have a working earth. There are some other lights and we're going to see them shortly as we do the live tests. So what I'm going to do now is turn on my failing overhead light. Apologies if it starts flickering, it's been doing that lately. And I'm going to plug in the tester here. You can see it's moaning, it's got less than 100 volts at the moment. So if we plug that in and then shut the flap, then we get an AC voltage appear there, and we can start doing some RCD testing. Now although this has an auto test, I'm going to go through the test manually just because the auto test is a bit fast, and I'm going to take it slow. We're going to do the 5 RCD tests to see if the numbers that come back are the numbers we expect to see. Now I should say that this is plugged in to an RCD protected circuit. There's an RCD back at the board of the circuit that this is plugged into. However, this is simulating an RCD, so it's not going to trouble the board, even though I'm sending a fault current to earth effectively to test the RCD. This is going to pick that up and it's going to react rather than the RCD back at the board, so I'm not going to interrupt the wife's watching of Strictly Come Dancing. Unfortunately, that's still going to carry on in there. So off we go. We're going to do first of all, we're on the 10 milliamp range. I've set the tester to 10 milliamps as the RCD I'm going to test, and we're going to send in a half times rated current. So we're going to send 5 milliamps down the line, and what should happen is this should not react. It should not be enough to trip that RCD, or that simulated RCD. Now this particular tester, the 1552, will perform that test for nearly 2 seconds before it comes back with a pass, assuming that there hasn't been a trip within that time. The regulations, I believe, state it's got to be able to take that for 300 milliseconds, if I remember rightly. And the the Fluke will test the 310 milliseconds, but the Megger here, it does go for nearly 2 seconds. So we're going to press the test button, and like I say, if the test is successful, this shouldn't trip, and that should show that we've got a duration of over 1999 milliseconds. So that was a successful test. And that's the half times test done. Now we're going to switch to the 1 times test, or the rated current test. So we're going to send 10 milliamps of simulated earth fault to this device, and we're going to do that at 0 degrees on the waveform, and we should see a trip within a certain time period. Now those who are familiar with BS7671 will know that an RCD to BS61008 should react within 300 milliseconds at rated current, or at 40 milliseconds at 5 times rated current. If it's an older RCD to BS4093, then those numbers are 200 milliseconds and 40 milliseconds. This is different because this is a simulation, remember, so we're not expecting the same kind of results, and what we are expecting here is a reaction within 40 milliseconds. So instead of the usual 300 milliseconds of leeway, we've got 40 milliseconds of leeway at 0 degrees. So we should see a number below 40 milliseconds. If we saw a result come back of, say, 50 milliseconds on this test, then ordinarily that would appear to be a pass because it's within 300 milliseconds that the British Standard recommends. But under the simulated conditions, it should react within 40 milliseconds, and if it doesn't, it's a fail. So we're going to squirt that in, and we should see a number below 40 milliseconds at rated current. And we're getting 36.4. Super duper. I'm just going to turn the light off again because we have another red light that's now appeared on here, and it says tripped. So I have to reset that from here in order to restore the voltage. Now I'm just going to change this to 180 degrees, so we're still at rated current, but we're now on the other side of the waveform, the AC waveform. Now again, the numbers change slightly here. The regulations state it should still be within 300 milliseconds, but the manufacturer's instructions for this say this test should be within 50 milliseconds, so it's slightly longer, but we need to see a result under 50 in order for it to be a pass. And if I press the button here, We'll see what it comes back with. 46.4, so super, that's passed. And if I just turn off the light here, we can see again it's tripped, and I can reset it by pressing the reset button. Okay, now I'm going to switch to 5 times the rated current. So we're going to send 50 milliamps down the line now, and we should see a trip occur within 10 milliseconds on this particular test. Again, it'd be 40 milliseconds in real life would be your upper limit. It's 10 milliseconds for the check tester here. So we're at 0 degrees again, 5 times rated current. Off we go. We want to see a result below 10, and indeed we get a result below 10. We get 7. I'm just going to turn the light off one more time because we're slightly different now. Not only have we got the tripped light on, but we've got a second light which says it's tripped at 5 times rated current. Reset that, and again I'm going to switch that to 180 degrees, and the numbers change again. Instead of it reacting within 10 milliseconds, it goes up to 20 milliseconds. So let's press the test button and we should see a result below 20. 17.0. Super. So that's all good. Now I'm going to do all this again, but this time at 30 milliamps, and this time on the auto RCD setting, just because it's a hell of a lot quicker and saves me having to push a load of buttons. Obviously every time it clicks off I've still got to reset it, but if we kick it off it's going to do its half times test. So it's going to send 15 milliamps down there, and it shouldn't trip within 2 seconds from what this tester records, and there we go, it's passed that. Now we're at 1 times 0 degrees. It's going to send 30 milliamps down there, and we get a result within 40 milliseconds like we want. It's 36.5. Now it's not going to do anything else until I press the reset button, and then it's going to automatically move on to the same test again, but this time 180 degrees, and we get a result within 50 milliseconds as before. Reset that again, it moves on to 5 times at 0 degrees, so this should be within 10 milliseconds, and it's 7.1. And the final test, 180 degrees at 5 times, should be within 20 milliseconds. Marvellous. Super. I'm not going to do the 100 milliamp test because obviously it's all the same stuff again. This tester does actually do 300, 500 and 1000 milliamps. The check tester does not, so I won't be able to test those ranges on this device, but I'm not too fussed about that because I can't remember the last time I tested an RCD above 100 milliamps anyway, so I won't worry too much about that until the time comes. So that's the RCD testing complete, and just to say, if you're not familiar with the Megger, once you've done an auto test on the RCD, you can press the red button there to cycle through the 5 numbers if you haven't already noted them down, so that works quite well. Dead simple. Okay, now we're going to move on to the loop testing. So I'm going to switch this to high loop. Now the loop on the... oh crikey, don't go yet. On the Megger here, the loop functions are on the green side of the dial, and there are 4 settings. On the right hand side we have high loop and high PFC, so this will do your earth fault loop impedance and your prospective fault current on a circuit that has no RCD, and give you the numbers for that. To the left of that we have the same tests, but this time it brings in the neutral on the no trip and the prospective fault for the earth fault loop impedance and prospective fault current. So you'd use those tests on the left side there if you were testing a circuit with an RCD on. Again, it's a moot point here because although there is an RCD on this circuit, this thing is going to intercept any nasties and not send anything down the line to trouble that. Now I will say that I'm expecting a high number here simply because this isn't plugged into where I normally plug it into. It's plugged into an extension lead to get it to where I need it to be by the camera. So we are going to see probably quite a high earth fault loop impedance. Normally I'd get a reading of sort of 0.79, something like that. This is a 32 amp type B 60898 ring, 2.5, 1.5, the usual nonsense, and for the upper limit for that, according to the regs, is 1.10 ohms. I'd expect to see a number below 1.10 ohms if I was doing a normal loop test from a socket outlet on this circuit. Like I say, I'm on the end of a extension lead, so it's going to be higher than the 0.79 or whatever I normally get on this circuit. It's going to be some way higher than that. It's quite a thin extension lead actually, it might even be significantly higher than that. So I'm going to switch this to loop, and I'm going to close the socket there to kick it off. The Megger kicks this test off automatically, unlike the Fluke, which you have to press the test button on. It gives you that beepy warning and then off it goes, and we can see it's actually come up with quite a high number there, 1.43. Now again, that's because I'm on an extension lead. I'm not too bothered about how high that number is, so long as when I plug the Fluke in under the same conditions I get the same sort of number. If both testers agree that that's the number on the end of this extension lead here, then that's fine by me. I can also perform that test of course on the no trip setting, where I should get the same sort of result. Certainly not too far off, hopefully, all things being equal. What was it, 1.43, and it's now, come on, 1.48. So a little bit of a discrepancy there, but not enough to keep me awake at night. I'm going to switch this now to loop plus 10 ohms. So from 1.43 we'd expect something around the 10.4 range, we're getting 10.7. And loop plus 180 ohms. Again, it should be consistent with what we're expecting to see. We're getting 180 ohms. And for the fault current test, I'm going to switch it to PFC. And on this circuit here, well, we're getting 21 amps. Again, may not be the kind of numbers you'd expect to see, but it's just because we're, like I say, we're on the end of a long extension lead here. But as long as the Fluke and the Megger both give me the same sort of reading, that's okay. If I do the PFC no trip setting, again, I should get that same sort of number again, somewhere around 21 amps. Wait for it. Blimey, it's enough to drive you to drink. Ah, yeah, there we go, 21 amps, jolly good. So that's the full gamut of tests that we can do with this thing. And obviously that takes us through most of the functions of what is a fairly basic tester here. Obviously other testers have far more functionality, things that we don't have here, like for example phase rotation or something like that. But all we're concerned about here are the basic tests, and that's good enough for monthly checks, annual calibration, and they'll test the full range of whatever test you present to them, or at least that's the idea. But I just want to know on a sort of weekly or monthly basis, are the basics, the nuts and bolts test I'm performing every day on continuity, RCD testing, earth fault loop impedance, insulation resistance, and all that sort of stuff, are they coming out as I expect? And that's what we use the check tester for. Well, not time strictly finishes. Oh, God, Bennett.